Jai Hind to all. My name is Vaishali Deshwal and currently I'm working as an assistant professor in CSE department of AKGEC Ghaziabad. So this is the fifth lecture on machine learning techniques and the code is KAI 601 and we are discussing the syllabus of machine learning technique as per the AKTU. So in today's session we will discuss that what is SVM, all the concepts related to SVM, what is kernel, what is hyperplane, etc. and genetic programming. Second topic will be genetic programming and all the concepts related to genetic programming. So let's start. So what is support vector machine? SVM is the most popular supervised learning algorithm which is used for both, for the classification also and for regression also. Primarily it is used for the classification, but it gives good results for regression also. So while we are using support vector machine for specifically regression, then it is known as support vector regressor. And the goal of SVM is to create the decision boundary. Decision boundary is nothing. It is a best line which can segregate the data into classes, into the different classes, as we are just classifying the data into the categories. So it can segregate n-dimensional space into classes, so we can easily put new data points in the correct category. The category can be true, false, or it can be male, female, etc. So this best decision boundary is known as hyperplane. So these are the concepts which are very important while we study support vector machine, like hyperplane, which hyperplane is to choose, what is margin, what is decision boundary. So decision boundary is the best line and the best decision boundary is known as hyperplane. Now how SVM creates hyperplane. So SVM chooses extreme points or vectors that help in creating the hyperplane, and these extreme points or the vectors are known as support vectors, as they are supporting or they are helping in creating the hyperplane, and thus the algorithm is known as support vector machine. So consider this particular diagram. This is a diagram showing a hyperplane. There these are the support vectors. So here, as we can see, there are the two classes, green and blue. So we have to classify a new data point, whether it will fall in this class or in this class 1 or class B, suppose. And these are, so we have to create the hyperplane. That is the aim, or that is the target. We have to choose the hyperplane. We can make this line also, this line also. There are a number of lines possible between these two data points, between these two classes, green and blue, but we have to choose the margin which is maximum, or you can say the distance, this distance should be maximum, or this is known as maximum margin, that we have to take the hyperplane in such a way so that this particular distance is maximum. This particular point is selected. Why we selected this particular point? Because this point is very near to the opponent class. Similarly, this particular point we selected because this point is very near to this particular opponent class. So these are the support vectors, and with the help of these support vectors we are just creating this positive hyperplane or negative hyperplane. These are the names you are giving to these particular lines, and with the help of these support vectors you are creating this hyperplane. So there are number of hyperplanes possible in this, but you have to choose the hyperplane which gives you maximum margin. So the SVM, it can be of two type. It can be of linear, it can be of non-linear. Linear, it simply means that where you can just draw a straight line, and where you just can't draw a straight line, that is known as non-linear SVM. So linear SVM is used for linearly separable data, the data which can be separated just by drawing a single straight line, which means a data set can be classified into the two classes, and such data is termed as linearly separable data, and thus here the name is linear SVM classifier. Non-linear classifier is for the non-linearly separable data, which means if the data set cannot be classified by using a straight line, then such data is termed as non-linear data, or classifier used is known as non-linear SVM classifier. Moving on, so these are some of the terminologies which we study in SVM. Hyperplane and support vectors, we have already studied that what is hyperplane, how to choose the hyperplane. So the hyperplane which gives you maximum margin is chosen as the best, and support vectors which helps to draw the hyperplane, they are known as support vectors. Now hyperplane, there can be multiple lines, there can be multiple decision boundaries to segregate the classes in n-dimensional spaces, but we need to find out the best decision boundary, and that helps to classify the data points, and this particular best boundary is known as hyperplane of SPM. Now the dimension of this hyperplane, it depends on the features. Suppose if there are two features, then the hyperplane will be a straight line, and if there are three features, then it will be a two-dimensional plane. So it depends on the number of features which are present. Now we always create a hyperplane that has a maximum margin. We have studied. So which means the maximum distance between the data point. As we have discussed here, that the distance between these data points should be maximum. Now support vectors. Support vectors are the data points which are very closest to the hyperplane, and I already discussed then how to choose this particular data points. This data point is selected because this is very near to this opponent class data points in comparison to all these data points, and we select this particular data point because it is very near to the opponent class in comparison to the other data points. Thus we select these two particular points and we just draw the line with the help of these points. These are known as support vectors. With the help of these support vectors, we draw the hyperplane, and thus these vectors, this support the hyperplane, and thus the name is support vectors. Next is kernel function. It is again, it is very important terminology in this algorithm. So kernel function, the main function of, or you can say the main aim of this particular kernel is that it transforms the training set of data so that a non-linear decision boundary is able to transform to a linear equation. For example, if I'm having data in 2D and I'm unable to separate it, or you can say that if there is a non-linear decision boundary, so I can transform it to a lower dimension, 1 dimension, or the 3 dimension can be transformed to 2D, so that the data can be arranged in such a way that it can be separate or segregated with the help of a linear line. So equation, so it is written here that it should be able to transform to a linear equation in a higher number of the dimension spaces. The type of kernels, the three types mainly. First is linear, then polynomial, and then RBF, or you can say radial basis function kernel, or the other name is Gaussian kernel. So linear is very simple. When the data is linearly separable, then it can be separated using a single line, as simple as. So it is one of the common kernel to be used, and it is mostly used when the large number of features. So these are some of the points which you should remember, that when to use which kernel. So if there are large number of the features which are present in the particular data set, then you should go for the linear kernel, and if the data is linearly separable, then obviously the choice would be linear kernel. So it is mostly used when the large number of the features in the particular data set are present. And one of the example I can give is text classification. Why? Because in text classification, each alphabet is a new feature. So we have a lot of features, and when the large number of features are there in the particular data set, then again we choose linear kernel, or it is preferable. So kernel functions, they are used as parameters in SVM course. So while you do coding in Python, then as parameters you will pass that whether the kernel is linear, polynomial, or Gaussian. So they help to determine the shape of hyperplane and the decision boundary. Next is the polynomial kernel. So it is the non-linear kernel function, and that employs the polynomial function to transfer the input data into the higher dimensional feature space. So it is opposite or very much different to the linear one. Third is Gaussian, or you can say RBF kernel. So it is the popular kernel function which is used in SVM. Again, it is the non-linear kernel function, but the difference between the Gaussian and the polynomial is that it maps the input data into the higher dimensional space using a Gaussian function. So there in the polynomial kernel we are using the polynomial function, but here we are doing the same thing, that we are just mapping the input data into the higher dimensional feature space using this particular function, that is the Gaussian function. Next we have okay, I think we have done this. So now the properties of SVM. SVM properties are maximum margin, non-linearity with kernels. What is maximum margin? That SVM aims to find the hyperplane that maximize the margin, and we have to choose the hyperplane which gives you maximum margin. Okay, or what is margin? That is the distance between the hyperplane and the closest data point from each classes. What is non-linearity with kernels? So SVM can handle the non-linearity separable data by utilizing the different kernel functions. You have the polynomial one, then Gaussian is there, which are the non-linear kernel functions. It transforms the data into the higher dimensional feature space where a linear decision boundary can be found. So this is again a property. Third property is support vectors. You know that what is a support vector and how to choose the support vectors. Then what is sparsity? It means the decision boundary is determined by a small number of support vectors rather than the entire training data set. Okay. Then what is versatility is that it can be applied. It is versatile. Why? Because it can be applied to the classification and the regression task both. In the introduction part, we have discussed that it is also used for the regression, and it gives very good result for the regression. And when we use it for regression, then it is known as support vector regressor. Okay, so control of complexity is that it provides a control over model complexity through the that you have the control. You can choose the hyperparameters again, that what to include, what not. Now what are the issues in SVM? Issues is scalability, that it becomes computationally expensive and memory intensive when we have large data set. Then lack of probabilistic interpretation. It means that in this we have the decision boundary which is known as a hyperplane that is used to separate the classes, but they do not directly provide you the probabilistic output. That probability means that what is a probability that a particular point is belong to, or you can say that whether a particular point belongs to class A or class B, that what is the probability of the belongingness to this particular class or that particular class. It doesn't provide you that. Then we have third feature, that is third issue, that is the imbalanced data. If while dealing with the imbalanced data, like suppose, I hope you understand that what is the imbalanced data set. So where the number of samples they're unequal. Okay, so SVM may be biased towards the majority classes. Suppose I am having true for number of features for like 1000 features, and I have false for only, or no as a target only for the 100. So you can say this is a imbalanced data, and SVM may show biased with such type of data. So interpretability is that SVM tend to provide good predictive performance, but they may not offer direct interpretability. Next topic is genetic programming. So we are done with the SVM, that what is SVM, what is SVR, what is hyperplane, how to choose it, what are support vectors, how to choose the support vectors, then what are the issues and what are the properties of the SVM. Now we'll discuss the genetic programming quickly, that and several concepts related to it, and it falls in unit 5 of MLT as per the AKTU syllabus. You can check. So genetic programming is a form of evolutionary computation. So we have already discussed the genetic algorithm, a short note, or you can say most of the concept like mutation, crossover of genetic algorithm in unit 1. Now we are studying genetic programming. So genetic programming is a form of evolutionary computation in which the individual, or you can say the gene, is in evolving population, they're the computer programs rather than the bit strings. So this is basically a comparison, that what is the difference between the genetic algorithm and the genetic programming. So in genetic algorithm, we have the individuals in the form of the strings. In the form of strings, I hope you remember, like 1 0 1 1 0 1. So in the form of strings we are having the individuals there, and we are performing the several operations like crossover, mutation, etc. But in this, instead of having this, we are having computer programs, and we have to perform the same operations on that also. So in 1992, COSA describes the basic genetic programming approach, and it presents a broad range of simple programs. How to represent the programs here? So they can be represented by trees. It is very important again that how to represent it with the help of trees. And there is the function call. It is represented by the node, a node you can say, in the tree, and the argument to the function, they're given by the descendant nodes. So these again, these are the nodes. Then, so you can say that the arguments, they are given by these descendant nodes. Okay, so as shown in this particular figure, this is a program tree representation in GP, and here you can see these are the nodes, and these are some mathematical operations performing on these particular nodes. So to apply GP to a particular domain, the user must define the primitive function. Okay, what are the primitive functions? So primitive functions to be considered as well as a terminal. So there are two things which we have to consider before applying the GP. For example, X, Y, and the consonant like 2, 3, 4. As you can see in this particular figure, there are some operations plus, minus. There are some numbers 2, 1, and variables like X, Y. So we have to define all these things before performing GP. And the prototypical genetic programming algorithm maintains a population of the individuals. You can say in case we have the program trees, we can have 2 trees, 3 trees. So on each iteration, it produces a new generation of individuals using selection, crossover, mutation. So all these things, that what is selection, crossover, and mutations, these are operations which we have discussed in GA, genetic algorithm. Next, the crossover operations are performed by replacing a randomly chosen subtree. So how to perform the crossover operation here? Let's see. So this is the tree, and this is again a tree. Now we can just cut, or we can choose any of the subtree, and we apply the crossover operation to the two parent programs, and we just swap these particular subtrees. So in this we put this thing here, and in this particular tree we put this subtree here. So this is a crossover operation. So the program is represented in the form of trees, and we apply the same functions here also as we are performing in GA. Now, the mode of evolution and the learning. Now, the mode of evolution and the learning. So, what is the mode of evolution and learning? There are some models in this. So, let's just move to the models. First model is the Lamarckian model. What are these models? So, in many natural systems, the individual organisms learns to adapt significantly through their lifetime. This is the main aim, or you can say, this is the main goal or aim of this particular model of evolution, that as a person evolves, then, or the organism evolves, then it learns to adapt during its lifetime something. Okay. First model is Lamarckian evolution. So Lamarck was a scientist, and in 19th century he proposed that evolution over many generations was directly influenced by the experiences of the individual organism during their lifetime. And he also proposed that these experiences of a single organisms, they also affect their offspring. So this is the concept which is proposed by Lamarck. Example, suppose if an individual learned during its lifetime to avoid some toxic food, so it could pass these traits on genetically to its offspring, which therefore would not need to learn the trait. Okay, so with the evolution, that person learns to avoid such type of food, and it just passes genetically to the offspring. So this is the concept which is suggested by the Lamarck, and this is known as the Lamarckian model. Now the second model is Baldwin effect. So although the Lamarckian evolution is not an accepted model, so other mechanisms, they have been suggested by the individual learning, and one of them is the Baldwin effect. So Baldwin proposed that individual learning can explain evolutionary phenomena, and learning smoothens the fitness landscape, and it facilitates the evolution. For example, some new changes in the environment of the species are happening, suppose, such as a new predator. So such a change will selectively favor those individuals who are capable of learning to avoid the predator. So it will benefit those individuals. Obviously it will benefit only those individuals who are capable of learning to avoid the predators. Okay, so we are discussing the Baldwin effect. So Baldwin provides an indirect mechanism for individual learning to positively impact the rate of evolution progress, and by increasing the survivability and genetic diversity of the species, so it increases the chances the species will evolve genetic and non-learned trends that better fit the new environment. So this is the concept, and this is known as Baldwin mechanism. Now there have been several attempts to develop this particular model or mechanism. For example, Hinton and Nolan in 1987 they tried to implement it. They experimented with evolving population with simple neural networks. So additionally, you can say some of okay, so we are discussing the Baldwin effect, and we have discussed that what is the Baldwin effect, what is suggested by him, and there are several studies which are done by the several researchers in 1987, in 1990, in 1994 to just implement this or to study this Baldwin effect. Next topic is, this is a small topic, that is the parallelizing genetic algorithm. So GAs, they are naturally suited to this implementation. GAs is genetic algorithm, and they are naturally suited this particular implementation. There are a number of approaches have been explored for this particular for parallelizing genetic algorithms. So first approach is coarse grain to parallelization. So it divides the population into somewhat individuals, into the number of small groups of individuals which are known as demes. Demes is nothing but the individuals. So each deme is assigned to a different computational node, and a standard GA search is performed at that particular node. Suppose there is a deme and that is assigned to a particular node, and on that node we perform the standard GA search. So these models, they are characterized by relatively long time they require for processing, and sometimes this approach, they are known as distributed GAs, because they are usually implemented on the distributed memory. So this approach is also well suited for heterogeneous networks. Okay, next is fine-grained approach. So fine-grained approach is the opposite to the coarse grain. So they require a large number of processors because the population is divided into the large number of small demes. So so here in coarse grain, we are just dividing the population into somewhat distinct group of the individuals, but while we are dealing with the fine grained, here we are saying that the population is divided into the large number of the smaller demes. So inter-deme communication is also there, either by this migration operator, or you can say the overlapping demes. So in this, you just need to remember the keywords, what are these particular concepts. That in general there are two approaches for the parallelization. So fine-grained implementations typically assign one processor per individual in the population, and recombination happens there among the neighboring individuals. So I think it is a good point to stop here, and in today's lecture, we have discussed the SVM, all the concepts related to the SVM, genetic programming, then the Lamarckian model, Baldwin effect, and then for the what can be done or what can be the algorithms for the parallelization. So let's stop here, and we'll discuss some more concept in the next session. Thank you.